Welcome to this Chapter 27 video, where I show how to implement locking within the producer-consumer model using pthreads mutexes. Let's go ahead and get started. So, back in my console here, let's go ahead and take a look at the changes that have been made. So I'm going to do git log -1-p. We'll put a stat in here too to show which files. And I'm only modifying thread.c. I've made really 24 changes here. Let's take a look at those 24 changes. The first thing I do is I actually add the pthread mutex. So I'm adding this to the data structure because the data structure actually shares this mutex between two threads. And that's the way it's supposed to be. Now, if we take a look at our producer is actually making some changes. We're removing that spin loop. That spin loop is a bad idea, so let's get rid of it. And we're going to replace it, since we're dealing with the free count here, we're going to replace that spin loop with a pthread mutex locks to start with. So the lock is going to lock that mutex. Now we can check free count without any possibility of a conflict between the two threads. So we're checking that. If free count is still less than 1, we unlock and then just as quickly lock it. So when I say that we removed the spin loop, we're still spinning. We're just simply doing more work in the middle of the spin. We're allowing the other thread to obtain the lock and possibly increment that free count for us before we lock it and check it again within our while loop. If our while loop is successful, if free count is greater than or equal to 1, then we go ahead and decrement it. We're still in a locked state here, and then we perform the unlock on this particular mutex. We don't change the actual buffer access. Again, this is not our critical section. But because item count is also a critical section code, we lock the mutex before we access it, and then unlock it when we're done. And you're going to see similar code here. We removed the naive spin loop. We add locking to our loop so that it unlocks and locks in our loop condition, and then unlocks after we modify. And then we also lock and unlock the mutex before we modify free count. Now, in order to use this mutex, within our data structure, I actually have to perform an initialize. So in here you can see I perform pthread mutex init on my mutex before I call pthread create. So with this change, let's go ahead and build our program. And if you remember last time, the program produced a lot of errors. Let's see if we produce errors this time. And no, we don't produce any errors whatsoever. So this actually runs fairly well. You'll notice a slight delay sometimes whenever I'm running this. So one of the things I did was, since I am checking this, I'd like to actually time my code. So I'm going to go ahead and check out a version that has the mutexes and as well as new timing code. And just taking a brief look at this, I include the header time.h. And so for each thread, I include some timing code that gets a begin and end using the time spec structure. And I call clock get time. I'm using the clock thread CPU time ID, so I'm only timing this particular thread. Clock get time allows me to read this at the beginning, read it after the loop, after the end of the loop, and then I can produce some results based on how fast that loop executed. And I do the same thing with the consumer thread. Just simply add some particular time. I finally got rid of that val equals 1, didn't need it in there. Then I go ahead and get time at end, and then print out the consumer runtime. So let's see with our, if we look at thread.c, we're timing our pthread lock that is spinning, unlocking, and locking before it performs the decrement. So let's see what timings we get out of this. So I'm going to go ahead and make this, run it, And what we see here is that this particular thread ran for 62 million nanoseconds. Now, nanoseconds is a billionth of a second. So really, this is 62 milliseconds, or 62 thousandth of a second. That's pretty good. If we run it again, it's about twice the speed now. It's 124 milliseconds. And really, over 100 is much more consistent than the 62 that we saw. If we might even consider this is about 110, maybe 120, considering the high end. So our average here, and I actually put this in my log, I calculated our average about 120 milliseconds for this particular run. That's not terribly bad, but again, we're using very inefficient loops, spin loops, to do this. There are ways to do spin locks. This is not one of them. We want to avoid just simply looping, unlocking, and locking all the time. So, next video, what we'll do is we'll try to figure out how we can do this and allow the threads to communicate to each other when a change is made to a variable. This brings me to the end of this chapter 27 video where I talk about pthread mutexes.